Hello class. This is going to be what I call my soft introduction to single value decomposition. We're going to start off with this picture. This isn't where mathematicians would start with this, but the slides give very little motivation, no motivation, and they just dive right in. And so I'm going to give some motivation on and kind of creep up on the single value decomposition. And we're going to do it by looking at this simple picture I made. So up here in the upper left, I have a simple picture, two kind of triangular shapes. And I could represent those as a matrix with just zeros and ones, where zeros are white and ones are black. This does generalize to grayscale. We could do grayscale things, and that would be really nice. Haven't figured out how to do that in a slick way in Excel. Gonna have to brush up my programming. So, so what I'd like to do, I would like to see if I could compress this a little bit and get most of the information with less data. And one strategy I could try is I could take the average of each of the rows. So equals, so here's the average. Oops. Looks like I have to brush up on my Excel skills. So here's the average of this row. Keep hitting backspace instead of enter. There we go. Okay, and so if I drag this down, that'll be the average of each of those rows. Notice this pattern makes sense. I don't have many ones at the top or the bottom, so the average is lower. I have lots of ones in the middle, the average is higher. I could also do the same thing with the columns. So I'm going to find the average of each of the columns. Okay. Now, here I have two vectors. I can think about these as two vectors, and just having those two vectors is a lot less information than having all of this, right? They cover the number of cells is quite different, right? There's a lot less with just those two vectors. And I can reproduce something with these two vectors in that's pretty close. And the way I do that is I will just multiply the average of the row by the average of the column to get each cell's value. So things that have a high number of ones in the row and the column will be really high. Things that will have a low number of ones in the row and column will be really low. And so let's try that. So I'm going to reproduce it right over here. But to do that, I need to copy this. Okay, now the easiest way to do the multiplication with this times this is actually just to do a matrix product, where I take this column and multiply it by this row. So notice this is not the dot product kind of product. These actually don't even have the same number of columns. I'm sorry, the same number of entries, so I can't even do a dot product with them. What I'm doing is taking this value, multiplying it by all of those to get one row, and then this value, multiplying it by all of those to get my second row. This is called what we call the outer product. So, so there we go. Now let's see how well we did. I'm going to shorten these up a little bit to help us. And to help us even more, why don't we Well, that's all right for now. Okay, so how did we do? Well, you can see that in each row, like here, if I look in this first row, I do go from something that's quite small to something that's the biggest value is in the middle, 0.127, and then I go back down. I do get this row of zeros, which corresponds to this row of zeros. What about my columns of ones? Sorry, it's a column of ones. Well, not the best. Not the best, although I get pretty high here in the middle with 0.8s and 0.6s. One of the things that might be happening, so here I have a total of, so if I highlight those, it says I have a sum of 32 down here in the bottom. If I highlight this, I have a sum of about 16. So I need to if I double all of these, then I'll at least have the kind of the same amount of stuff floating around in the matrix. So, because some of these values are kind of small, like none of these are 1, and some of these values are larger than 0. You know, they're all larger than 0. I didn't get anything larger than 1s. So why don't I double this? And now, now I can, if I highlight this, I get a sum of 32, and here I get a sum of, well, 32 something point something, and there I get 32. So now at least I have about the same number of, the same total value that I'm spreading out over the same number of cells. And here, it's a little bit nicer now, because here I can see I've got some values over 1. Here I've got values that are, that 0.952 and 0.952 is quite close to 1. This is quite high, 1.778. These are still low. I mean, I'd like that to be 0. So one thing, just to get a general idea of how we're doing, we could I'm just going to have it round quickly and see how well we did. Oh, hey, that's not bad. So just rounding to the nearest one, we see we're way too big here. But the other values we're off of is this one, and this one, and then similar corresponding ones over there. That one, and that one. Okay, so with just rounding, it's not too bad with what we had. Of course, these aren't really 0, these aren't really 1s, but just to kind of get an idea about how good that strategy worked for us. Let's go back to format the cells. I'll just do 2 decimal places now. Okay, so this is a nice thing. So, but we didn't get it exact, and there's a really nice structure to this picture. If we didn't have such a nice structure, this attempt wouldn't work so well. But what we could do is we could try a similar thing. And what I mean a similar thing is, what if we could find another matrix, another vector that's this length and another vector that's this length, and multiply them together. Maybe we could do that over here. So if we could find another vector and put them over here, these corresponding vectors, I think I went too long. And do that same thing, we could create another one, another matrix, and that time, this matrix, we'd like to correct some of the errors in the first matrix, and then we could add them together. And that should get us closer. And then, if that's not close enough for us, we could do it again and find a 7 length vector plus a 9 length vector, I think is what it is. Multiply them together, scale it. Remember, we did scale this, but we multiplied this one by 2. It made sense to do that. And then we get another one and we get added together. And that would be really nice if we could just do that a few times and get lots and get basically the same picture out. This is kind of this is a poor man's version. What I did here, there's not a great poor man's version that I know of to get the second one. But this idea of taking a matrix and breaking it up into scaled outer products, that is the core of single value decomposition. And although the book starts it in a different way, they don't talk about the outer product first. They'll talk about the inner product. I'm sorry, not the inner product. They'll talk about it in this factorization. They'll take a matrix and we'll factor it down into these three special matrices, which we'll talk about. What we've been doing is trying to write a matrix as this outer product form, where we had two matrices, two vectors. We multiplied them together in an outer product, and we scaled it. That's the sigma 1, and we got something that was close to A, but it wasn't exact. And so maybe we could add another scaled outer product and get it to get closer to A. And if we can get almost all of A with just a few of those outer products, then that can save us a lot of time and information and storage space. So yeah, it could save us a lot of bandwidth if we're transporting that information, etc. So in practice, that's one place where this comes into play. The other place is it helps you to see the structure of something that might just be too big and wieldy. So for example, if we go back to this picture, this corresponds to basically what I'm talking about is this right here. This vector corresponds to basically the first important vector. One of these vectors right here, U1 or V1 transpose. It turns out to be something close to U1. And here, this is close to V1 transpose. And this tells you something about the structure of what's going on. It looks like there's lots of ones in the middle and not very many ones on the outside. Now we can see that just by looking at this picture, but just by looking at the small matrix. But when you're dealing with a very large data set, that might be hard to see. And here we can see that this tends to increase in the amount of stuff that's there, and then it drops off to 0, and then it increases again. So there's a pattern going across the right. So these tell us important information about the structure of the data set or the matrix that we're dealing with. So that's another really important feature of the single value decomposition. So if you Google single value decomposition online calculator, you can find calculators that will do this for you. And the best one that I've found, one of the really nice ones that I found, is this one at comnuon.com. And what you can do, here, I'll reset this so you can see, is you paste in or type in a matrix. Doesn't have to be zeros and ones, can be any matrix. This one is nice because it does some pretty big ones, so you can do real applications with this. So the other ones, it limits you to sizes of like 7 or 8. For your homework, you're going to be dealing with things like by 2 by 3s and things like that. They're not going to be very big if you do these by hand. And if you hit calculate, then it resets and it pulls up some information. And so I'm going to copy all of this information, and let's put this into Excel over here. So these didn't go into matrices. These didn't go into the cells. So I'm going to do a quick text to columns, and okay, now I have those in actual cells, so I can deal with them. So the single value decomposition, this tells us it looks like there's three important pieces for the single value decomposition. There are three important pieces. They are you can think of these as the sigmas. Those are what are called the singular values. Those are right here. Okay, those are the singular values of the matrix A, like this picture matrix that we have here. And then there's U vectors, and there's V transpose vectors, or you can think about them as V vectors. We have U vectors and there's V vectors. And one of them corresponds to vectors going up and down, kind of like this one. So they're the same length as the number of rows, and that turns out to be U. So here we have 1, 2, 3, 4, 5, 6, 7, and that's the number here we have 1, 2, 3, 4, 5, 6, 7. And V, the V matrix corresponds to there's a vector for every column. So sorry, my wife's trying to call me. Should have turned down my ringtone. All right. Okay. So there's one of these for every. The length of these is the length of a row, and there's one for every column, and so there are nine vectors, if I counted right. Yeah. So there's 9 vectors here, and each of them is of length 9. Here there are 7 vectors here, and each of them is of length 7. And we'll talk about how to get these by hand. But first, so the U1, U2, U3, U4, etc. Those are this column. This is U1 right here. So this is U1, and this is U2, and this is U3, etc. And these are V1, V2, V3, okay, etc. Now, to try to convince you that what we were doing up here actually does seem to correspond with the single value decomposition, I'm going to use U1 and use V1, and I'm going to multiply them together in an outer product, and I need to scale it by this singular value here, which is very similar to what we did. We had an outer product and then we scaled it by a value, although mine was 2. This one turns out to be 5.13. And we're going to do this, and let's see how close we get to this matrix. So here's that one. I have to transpose this. Okay, so notice these are negative. Negatives are fine. They scale when they do the decomposition. They make it so the singular values are all positive, and sometimes that means that you get vectors that are all negative. That's okay. You will see though that this vector here, this U1 here, it does seem to follow the same pattern that we had with our makeshift one. Right, it's symmetric, and it starts low, goes up, and then comes back down. Doesn't go up as high. There's not as big of a jump from like this the third one to the fourth one as we had, but it still holds the same pattern. And this still holds the same pattern that we saw with ours up here. So you can see that it starts small, gets larger, gets up to 1, and then drops down to 0, and then does the same thing. Here it does start small in absolute value, gets larger, larger, larger in absolute value, not up to 1 like we saw, but drops down and then does the same thing. So, so it seems like our strategy that we tried doing it one time, this might convince us that it's pretty much doing the same thing. Well, a similar thing. I shouldn't say the same thing. So let's take the outer product, and I want to scale this. So scale by 5.13 or so. 5.13. Okay, so that's multiplied all those by that. And yeah, now we can compare what we did up here to what we got down here. And it looks like we are, looks like someone didn't do a good job of this. Let's delete these so we can get them all on the screen. So the pattern looks similar. So we get small values in the corners. We build up to our largest value is in the same spot. We're not as far off here though as we did with our strategy. We get 0.9. We're a little closer with these three than we got with ours, so that's nice. We're a little further off though with some of these values. So we were a little closer to our zeros here. They're a little larger, so they're closer with some places and not so close in other places. It's still symmetric like ours, so hey, not bad. We could try to do what we did before and just round it and see how well we do. Oops. And looks like we didn't do as well. We did do better here. We're not up to 2, but we didn't do as well here. Like we lost these, bumped over to, they went up to 1. Because here they were at 0.38, so they went down, but here they're barely over 0.5, if I remember right. So, but similar idea. Yeah, so we're like right at 0.5 or just a touch over. So, so it didn't help us there. So, but not bad. But what this does is this helps us to know what the next one could be, and the next matrix to help us out would be taking the outer product of U2 so we can take U2 here, and we can take V2 here. Oops, gotta transpose that. Okay, take the outer product, that vector times this vector, and we need to scale it by the singular value, 1.8. So I just have to multiply that by 1.8. And there we go. And here we can see that it's going to help us sum, because if we add this to this, then look, this this is going to subtract values where we're too high. Look, so right now we're too high right here, right? Those are all zeros. So it'll help to subtract down. It also subtracts down right here where we're too high. We were up at 1.26. So in fact, across the board right there, we're a little high. So it's going to subtract off some, get us closer. And places where we're too low, maybe like right here, the 0.1644 and 0.16 is going to add because we're a little low. We want these to be 1, and we'd like them to be higher. We'd also like to add this one. We'd like to get this to 1, and it's going to add something there. So this is going to help us get one step closer. How did it find these? We'll talk about that in the next video. But one thing that it does is this decomposition is we don't just pick any vectors here to deal with. We're going to pick orthogonal vectors. That makes our next move the most efficient that it can be. So this vector here is orthogonal to this vector right here. Not only orthogonal, they both have a length of 1. So that they're actually part of an orthonormal basis. So if we do the dot product with those, we should end up with zeros. And same thing with these. This vector here and this vector here, they have they are orthogonal to each other. So if you take the dot product of those, it should be 0. So and so each time we're kind of doing the most efficient thing, we're going to pick the next one, pick another one that's orthogonal, and that kind of gives us the most bang for our buck. And then we get to find the next one and the next one. So that's what these are. And how to find those actually is pretty slick from a computational perspective. By hand, it's crazy. It uses a lot of the skills we've learned so far. It is straightforward, but it is kind of long. But there's one more thing I want to do before I end this video, and that is I want to make sense of this one. So I want to make sense of this structure right here. So U sigma and V transpose. It says A should be able to be written as a product of these three matrices. We've seen U and V. We've seen U and V. This sigma, it is the same size as A, and it has zeros everywhere except down the diagonal. What you'd think of as the diagonal if you start to the upper left. And the values down the diagonal are the singular values. So let's go back and let's try to write all of this and see how it looks in Excel. So we have the singular values here, and we have U. So here, I'll just copy U down here. Okay, so here's U. The size, that sigma matrix is the same size as our original matrix. Okay. So this is sigma. I use that capital sigma. Now it's not the original matrix, but I just did this so we could easily get the size right. And I'm just going to fill this all with zeros, and because this is where we start with that matrix, and then I use these singular values to finish it off. So this equals this singular value, and then I'm thinking down the diagonal, so this equals this singular value, and this equals this singular value, and this equals this singular value, and these last singular values are all 0, so this is as much as I can do. And one thing this tells us is that we have some redundant information in here, and in fact I can get all, if I understand this right, I only need 4 vectors of u and 4 vectors of v to get all the information in our matrix. So yeah, if I understand right, that's what we need, all we need. So now let's put v transpose over here. So I'm going to highlight v, copy it. And I'll paste the transpose. So here's v transpose. So here you can see, you can kind of see we're going to get the outer product because we'll do this times this, and that's what we did in our first outer product up here, right here. So yeah, it might be hard to see initially right here, but that's what's going to happen. It'll just be scaled. So let's actually do this multiplication and see if this makes sense. So I'm going to multiply this matrix by this matrix. And I get a matrix. Notice that matrix is the same size as our data matrix again. So this was 7 by 7. This is 7 by 9. Sigma is 7 by 9. And V is 9 by 9. So if I multiply a 7 by 7 times a 7 by 9, I'm going to get a 7 by 9. And if I multiply a 7 by 9 times a 9 by 9, I'm going to get a 7 by 9. So, so the size works out, luckily. So now let's do one more product where I'm going to take this matrix, which is my u times my sigma, and multiply it by v transpose. And notice we have a lot of zeros here, so like all the important information's over here. So equals matrix multiplication of this. The zeros are important in the sense that they allow us to do the multiplications for the right size. So these are good examples of what the book's called partition matrices, because you can see like there's nice blocks already. So okay, so we multiplied that out. This is u times sigma times times v transpose, and you'll say, Brother Corey, that's not exactly the same. It's not, because the computer can only go so far and we get round off error. But you can see the ones are all, the things that were ones are all very close to ones, and the things that are not ones are are really close to 0. So now here's the thing. How close are we if I don't, if we only use, if I change this to 0, then we really just used the first 3 u's and the first 3 vectors of v, the first 3. And we get pretty close. Like we're all pretty close to 1 where our 1's are, and we're pretty small, much less than half at least. That 0.23, those 0.23s kind of are off by a little bit. But that would be enough if we rounded. So if we format the cells, if we round, we're still okay. How about if we only use 2, how close do we get? If we only use the first 2 vectors, and look, rounding, oh, we're super close, we're only missing these values right there. So, so we don't need the whole data matrix. We actually just need 3 things, 3 vectors this length, and 3 vectors this length, and 3 values in here, and that's enough for us to reproduce this. And our rounding will get us exactly what we want. We're really close with 2. So, yeah, so when those of you that are in 215, I believe your last lab, you actually do this with an actual image where you'll compress it using the first few or several single value decomposite single values. So you notice there's a drop off, so that 5 to 1.8 is pretty big. This one isn't as big. This one isn't as big. There's a huge one, but so sometimes you get massive drop-offs, and when you do that it means like that next one's not going to add nearly as much information as that first one. I did an example with where is it? Oh yeah, so I did an example with some stock prices, and you can see that from the first to the second one, the single values drop down by a factor of 100. So almost all the information is captured in that first one. So anyway, it's an example. Okay, let's see. What did I miss? We better stop there, and then I'll create another video and show you how to actually go through the procedure and do it by hand and talk about some of the nitty-gritty details. Thanks.